Welcome back to the deep dive. Our mission here, as always, is to take this just overwhelming amount of information,
Yeah.
the tangled mess of global reports, scientific papers, regulatory updates, and really distill it down into clear, usable knowledge for you.
And today, we are tackling what you could call the packaging paradox. I mean, we live in a world that demands these ultra-high performance materials to keep our food safe, extend shelf life, and protect, very complex products in a global supply chain.
Right.
And yet, at the same time, we're facing this existential crisis driven by plastic pollution that threatens pretty much every ecosystem on Earth.
It's the ultimate tension, isn't it? The old linear system of take, make, dispose has completely hit a wall. And not just environmentally, but financially and, politically, too.
Yeah.
Our sources for this deep dive reveal a massive and, really rapid transformation.
It's a huge shift.
And it seems to be driven by two forces just colliding. You have breakthrough material science on one hand, and on the other, these aggressive, almost non-negotiable global regulatory timelines that are focused squarely on 2025 and 2026.
That's exactly right. We're not just looking at simple alternatives anymore. We're actually observing the creation of entirely new circular economic loops. So our exploration today is going to focus on two really powerful solutions.
Okay.
First, how these huge volumes of existing agricultural waste are being converted into extremely high-value industrial goods. And second, how we're pioneering new, genuinely regenerative materials that are harvested directly from the ocean.
Okay, let's unpack this. Our goal today is to give you a shortcut to understanding this confluence of forces from the UN Plastics Treaty that's forcing a conversation on chemical limits to the really specific polymer requirements being set by the EU's packaging and packaging waste regulation, and how waste materials are, amazingly, becoming the premium feedstock of the future.
We're tracing the shift from, simply managing pollution at the end of the pipeline to actually designing for regeneration and circularity from the very, very beginning.
So when you think about the sheer scale of global agriculture, the waste that's produced is it's staggering. We talk a lot about food waste, which is, of course, critical, but what about all the non-edible byproducts?
Exactly.
Let's take rice husk or rice hull as our prime example here. In massive rice-producing nations like India or China, we're talking about millions of tons of this stuff generated every single year.
And traditionally, that rice husk was just a severe disposal problem.
Yeah.
It was managed by, burning it, which releases CO2 and particulates into the air.
A huge air pollution issue.
A huge issue. Or by dumping it, which occupies massive amounts of landfill space. It was a secondary pollution crisis, really, just a cost center that farmers and industry had to manage.
Right, a liability.
A total liability. But now, government policies globally, and I point particularly to India with its waste-to-wealth focus, they've provided the essential market signals and the incentives to flip this script entirely.
So it's not just that the material is available in huge quantities, it's that the regulatory and the financial structure now exist to support treating it as a raw material of really high value.
Precisely. And what's so fascinating is the sheer spectrum of high-demand industrial outputs that you can extract from rice husk and its resulting ash. It's not just one product, it's a whole 360-degree utilization model.
So let's start with the chemical production side, because this is where the highest value is often generated, right? What critical industrial components are we pulling out of what was essentially chaff?
Okay, so the primary output that's really commanding global attention is precipitated silica. Silica is, it's ubiquitous. It's used in rubber manufacturing and plastics, compounding, paints, all sorts of chemical processes.
So it's everywhere.
It's everywhere. And the key advantage here is the sustainability credit. Industries that are committed to decarbonization are prioritizing rice husk ash-derived silica because its sourcing and its processing require significantly less energy and chemical input compared to, say, mining silica from quartz or sand. That instantly makes it a premium, eco-friendly input.
And that ties right back to the regulatory pressure we're going to talk about later, where sourcing sustainable inputs can literally reduce a producer's environmental fees.
Absolutely. They're directly linked. Then you have something like oxalic acid. This is another high-demand commodity chemical globally. It's essential for cleaning agents, textiles, metallurgy. Companies that use rice husk as the feedstock can produce it much more cost-effectively and sustainably.
So that gives startups an immediate leg up.
An immediate one. It gives them export opportunities right out of the gate, particularly in the highly compliance-sensitive markets of, say, the Asia-Pacific region and Europe, because they can offer a certified sustainable origin for their product.
And the high-tech angle. The silicon extraction. That seems like a particularly lucrative
Oh,
niche.
yes. Silicon extraction from rice husk ash
Hmm.
is gaining a lot of prominence because of its purity and its cost effectiveness. Silicon is vital for electronics, solar panels, specialized construction materials. Husk ash offers a preferred, low-cost raw material source compared to the traditional methods. We are seeing these niche, high-profit startups emerge that are dedicated solely to this extraction because the demand worldwide for electronic-grade low-carbon silicon is just skyrocketing.
So we've got high purity inputs for electronics and then these bulk chemicals. What about the necessary industrial workhorse chemicals like sodium silicate?
Sodium silicate is a perfect example of how efficiency drives value.
Hmm.
It's used everywhere as a binder in detergents and adhesive, a critical component in construction. When you manufacture it using rice husk, the process is inherently cheaper.
Okay.
That ensures long-term margin stability and profitability because your raw material supply is massive, it's reliable, and it's basically subsidized by its status as a waste product. And we can't overlook furfural. It's a building block for solvents, plastics, resins. The chemical manufacturing industry prefers this sustainable route, and that creates immense profitability for medium-scale plants that are focused on export. The source material itself grants a competitive edge globally.
And that strong demand signal clearly crosses over into construction materials, which are, incredibly high volume and often have a massive carbon footprint when they're made traditionally.
That's the next logical step, exactly. Driven by global urbanization, there is this continuous huge demand for things like hardboard and MDF, that's medium-density fiberboard. When these panels are made using rice husk composites, they are fast-selling, eco-friendly alternatives that guarantee bulk demand from builders who are seeking greener certifications for their projects.
And it goes all the way down to the literal blocks and bricks used in housing.
Indeed, particle boards and building blocks or bricks that incorporate rice husk ash are inexpensive. They significantly reduce the material cost of construction while being environmentally friendly. This combination is actively supported, even prioritized, by governments that are pushing for sustainable building materials and low-cost housing initiatives.
And what about insulation?
Well, the push for energy efficiency makes rice husk-based insulation materials highly sought after for both construction and electronics, which really secures their future demand.
So the material literally goes from being landfill fodder to high purity silicon, and then circles all the way back to become the fuel that powers its own processing.
That's the closed-loop ideal. Instead of being burned inefficiently as waste, the husk gets channeled into monetized clean energy sources. Rice husk briquettes, for example, offer a very cheap fuel alternative to coal for both industry and for households. Startups that focus on briquetting can have extremely low initial investment costs, but secure a steady income from large industrial clients who are looking to shift away from dirtier fossil fuels.
And the high-spec export market for energy. That comes in the form of pellets, right?
Correct. Rice husk pellets are recognized internationally as a clean energy source. They are extensively exported, particularly to Europe and Asia, for use as industrial boiler fuel. And the viability of these markets is underpinned by strong renewable energy policies and carbon taxation schemes, which makes them highly profitable export commodities.
And then finally, the part we all see, the consumer-facing goods. This seems like the easiest entry point for a lot of new companies.
It's definitely the most visible success story of this whole waste-to-wealth model. Biodegradable cutlery, plates, and cups. These are now internationally popular replacements for traditional single-use plastics. The global export market for these products is just being driven directly by consumer sustainability trends and bans on conventional plastics. It offers massive growth potential.
Let's just pause on rice for a moment, because this whole waste-to-wealth idea applies to so many other crop waste streams around the world. Our sources highlight some fantastic work being done with coconut husk fibers, or core, specifically by companies like Essentium Materials.
The coconut example perfectly illustrates what you could call the triple benefit. You get environmental impact, material performance, and social equity, all from this one circular model. Globally, coconut farming is a massive industry, but an estimated 85% of the husks are typically just treated as pollution. They're either burned or left to rot.
So a similar problem to the rice husk.
A very similar problem. Essentium takes these core fibers and converts them, often blending them with recycled plastics to create a really high-performance composite.
And what are the performance characteristics when you blend a natural fiber waste with recycled polymers? What happens to the material?
Well, the resulting cocoa poly material is chemically and physically superior to many of the traditional all-synthetic alternatives. It's demonstrably stronger and stiffer than equivalent glass fiber or pure plastic compounds.
Wow.
And crucially for manufacturers, it's cost neutral. You achieve superior performance without having to pay more for your raw materials. Plus, core is naturally high in something called lignin, which imbues the composite with antimicrobial properties, a functional benefit that is highly sought after in things like cutting boards or food transport containers.
The environmental payoff cited in the research is just huge. Can we talk about the hard number?
We can. If this core composite successfully replaces synthetic polyester fibers in all the relevant applications, researchers estimate the annual reduction in petroleum consumption would be somewhere between 2 and 4 million barrels.
2 to 4 million barrels.
Yes. And on top of that, it would curb carbon dioxide emissions by approximately 450,000 tons every single year. That's a massive climate dividend generated simply by utilizing a waste product.
But the human equation here, the social impact, is arguably the most compelling part of this story.
It truly is. It changes the whole conversation about what sustainable sourcing really means. The successful adoption of these waste materials could potentially double the annual income for the estimated 10 million coconut farmers worldwide.
Double their income.
Many of these farmers are at a subsistence level, often earning less than $2 a day. So by creating a reliable, high-value demand for their waste product, you elevate their economic stability from the ground up. This isn't charity. It's a functioning market creating shared value.
That statistic, doubling a farmer's income from a waste product, that really is the key leverage point. It moves waste from being an environmental liability to a powerful social and economic asset.
And this material is already in industrial use. We're seeing this cocoa poly in high-spec engineering applications like automotive parts trunk liners, load floors, and increasingly complex battery pack covers for electric vehicles, where stiffness and lightweight are critical. And it also spans to consumer goods like cutting boards and specialized living wall planters. The diversity of application really proves its industrial viability.
So that really establishes the optimization pillar, taking existing waste and just wringing maximum value from it. Now let's transition to that second pillar, creating entirely new, inherently regenerative materials from the world's largest resource, the ocean.
The immediate reaction, when we discuss bio-based inputs is often to focus on the traditional bioplastics, the ones that are derived from corn or potatoes or wheat starches. They're the ones that dominated the early market.
Sure.
But there is a growing and I think justifiable skepticism about their long-term environmental viability when you try to scale them up to replace plastics globally.
If they're plant-based and biodegradable, what's the fundamental environmental flaw? What's the problem?
Well, the flaw lies in the agricultural model itself.
Mm-hmm.
Scaling up these traditional feedstocks demands enormous amounts of resources. We're talking massive freshwater consumption, dependence on chemical-intensive crop production, which causes nutrient runoff, and just immense pressure on land use.
Right.
This pressure risks driving monocropping, soil depletion, and in some cases even deforestation. Project Drawdown, for instance, classifies traditional bioplastics as an area to keep watching, noting that scaling them up by the required 30% per year could really start to strain global food systems.
And here's where marine algae, or seaweed, presents a fundamentally different model. It bypasses almost all of those land use pitfalls.
It is genuinely transformative. The advantages are all rooted in its cultivation. Seaweed requires zero fresh water to grow. Its cultivation happens in the ocean, so it completely eliminates reliance on arable land, which is essential given global population growth. And crucially, it can be grown without the need for pesticides or synthetic fertilizers. That solves the chemical runoff problem inherent to land-based monocultures.
And the potential for it to be a restorative crop, not just a neutral one, that's the truly compelling narrative here.
The potential for restorative aquaculture is arguably the biggest selling point. Thoughtfully cultivated seaweed can provide net positive benefits to the marine environment. It actively absorbs excess nitrogen and phosphorus, helping to mitigate coastal ocean eutrophication, the creation of these oxygen-depleted dead zones.
Wow.
It can potentially reverse local ocean acidification by absorbing CO2, and it strengthens biodiversity by providing essential three-dimensional habitat for juvenile fish and invertebrates.
It sounds utopian, but that word thoughtfully seems critical. How do we ensure that scaling up seaweed farming doesn't just create another industrial monoculture problem, but this time in the ocean?
That is the crucial challenge, and it's one that researchers and organizations like the Nature Conservancy really emphasize. We cannot simply industrialize the sea. Farming has to adhere to these strict principles of restorative aquaculture. This means extensive research into site selection, choosing areas where nutrient absorption is most needed.
So you can't just put it anywhere.
Exactly. It means culturing diverse native species that align with local ecological processes, rather than just choosing the one fastest growing variety. If the primary driver is purely yield maximization at the lowest cost, we risk introducing diseases, or altering local currents, or even depleting nutrients too aggressively. The regulatory frameworks we discussed have to mandate these restorative practices, not just allow for marine inputs.
So let's move from the farm to the film. What are the material science properties in seaweed that actually allow it to be turned into a bioplastic film?
It all comes down to the complex carbohydrates that are inside the algae cells, the polysaccharides. These are long, flexible sugar chains, and once you extract them, they can be cast or molded into films. Different types of algae yield different polysaccharides, and that results in huge variations in the film properties, particularly mechanical strength and barrier capabilities.
Let's break down the main families, maybe starting with brown seaweed.
Okay, so brown seaweed is the source of alginate and fucoidin. Alginate is the most established. Its films are already used as edible coatings to extend the shelf life of highly perishable items. Things like fresh-cut apples, strawberries, even minced beef or specialized cheeses.
So it's already in the market.
It is. Now, fucoidin-based films are technically interesting because they exhibit some of the better water vapor barrier properties among the seaweed films. They often achieve orders of magnitude around 10 to the minus 5 to 10 to the minus 7 grams per meter per day per pascal.
And what about the red seaweed family?
Red algae give us agar and carrageenan. Agar is crucial because it forms these strong thermo-reversible gels. This means it sets when it's cooled, but you can melt it and reform it just by heating it up, which is incredibly useful for high-speed industrial processing. It allows for precise molding and consistent film thickness.
Okay.
And red algae films, in general, offer the most consistent WVP barrier properties, typically landing in the range of 10 to the minus 4 to 10 to the minus 6.
And carrageenan specifically, that seems highly adaptable.
It's the chameleon of the seaweed world, really, because its function is dictated by the chemical structure of the polysaccharide and how it interacts with cacodynes like potassium or calcium. Kappa-carrageenan forms very strong, rigid gels. Think of it giving you that stiff, rigid container feel.
Right.
Iodocarrageenan forms weaker but significantly more elastic gels, which is essential for stretching films. And lambda-carrageenan is typically non-gelling. This versatility means a manufacturer can tailor the exact blend to match the needs of the product, using a rigid Kappa blend for a carton liner or an elastic iota blend for wrapping soft cheese or liquid-filled pouches.
Now let's talk about the hard wall these materials hit when they face commercial requirements. Because despite all this progress, they aren't ready to replace all plastics yet, and that's primarily because of two major technical hurdles.
The first, and honestly the most significant, is the water vapor barrier, or WVP. This is the measure of how well a material stops moisture from passing through it. It's the key to shelf stability for any dry goods.
And what's the performance gap here? Can you translate those scientific notations for us?
Sure. Seaweed films generally have low to moderate WVP properties, typically in that 10 to the minus 3 to 10 to the minus 5 range. Now, this is fine for keeping a slice of cheese or an apple from drying out quickly.
Yeah.
However, dry commercial food packaging, think powdered milk, coffee, potato chips, or any shelf-stable snacks, requires WVP values in the ultra-low range of 10 to the minus 7 to 10 to the minus 9.
So to put that in perspective, that gap of 2 to 5 orders of magnitude, that's like the difference between wrapping your powdered coffee in a thick, semi-breathable t-shirt versus wrapping it in heavy-duty aluminum foil.
That's a perfect analogy, the fundamental performance difference. Until material science can close that gap, seaweed films are really limited to these niche applications, like fresh food coatings or very short shelf life items, not the global dry food supply chain.
And the second challenge relates to mechanical stability, specifically elasticity. If the film can't stretch, it just breaks on high-speed industrial machinery.
That's measured by elongation at break. Well, the film's tensile strength, so how much pulling force it can withstand, often meets the 10 megapascal minimum for food packaging. Its elasticity is the major flaw. Elongation at break for current seaweed films is typically very low, ranging only from about 2% to 30%.
Why is 30% elasticity not enough for commercial use? That sounds like a decent amount of stretch.
Because the high-speed form-fill seal machines that package most of our food rely on the film, having a really high degree of flexibility and stretch to absorb stress during the sealing, shaping, and handling process. Packaging for products like fresh meat or liquid pouches or powdered goods requires extremely high elasticity, with elongation at break ranging from 100 to 600%.
Wow.
So if a film can only stretch 30%, it simply won't survive the production line or the shipment journey or even consumer handling. It would shatter instantly.
But the industry is making some smart moves, capitalizing on the material's current strength, which is its end-of-life benefit. Companies like Sway, who are partnering with Eco-Enclose, are focusing on applications where high barrier properties are secondary to certified compostability.
That's the strategic approach. Sway utilizes its seaweed-based film, which they call TPC. It's 50% or more seaweed content, and they target flexible applications where the material's rapid safe degradation is the primary value proposition.
And that includes things like clear poly bags and these specialized applications like film windows.
The film window for retail boxes is particularly brilliant. A traditional plastic window contaminates the paper or cardboard packaging, which means the entire box is usually unrecyclable and just goes to the landfill.
Right, I've seen that.
But using a certified home compostable seaweed film window, the paper box can be recycled without contamination. It solves a long-standing structural problem in the recycling stream.
And their end-of-life guarantee directly addresses that intense public demand to avoid greenwashing.
Absolutely. The material is designed for home compostability, and it's undergoing the rigorous TUV home compost certification right now. Furthermore, independent testing verifies that the film is marine biodegradable. This means they are mitigating the environmental impact at the beginning by choosing a regenerative ocean input, and at the end, by ensuring that if the product mistakenly leaks into the environment, it degrades safely without contributing to persistent plastic pollution. What's really fascinating here is that innovation alone, while it's necessary, is just not sufficient. The rapid transition from the traditional linear plastic economy to a circular model is being forcefully accelerated by global mandates. For any company today, compliance is no longer a peripheral cost. It is the absolute, non-negotiable key to market access and profitability.
So let's start at the very top with the UN Global Plastics Treaty. The negotiations are often, deadlocked, but the intent remains massive, addressing the full life cycle of plastic.
The initial resolution, which was passed by 175 nations, aimed for implementation as early as 2025. The core idea is unprecedented, establishing legally binding international rules that address the entire life cycle of plastic, from the chemicals and production limits right through to disposal, not just waste management at the back end.
The recent negotiation meetings, INC4 and INC5, have been extremely challenging. What are the non-negotiable red lines for the coalition that's pushing for an ambitious treaty?
Well, there's a unified coalition of over 100 countries, including the entire EU, the UK, Canada, and many nations from Africa and Latin America, and they're demanding 4 non-negotiable points.
Okay.
1, the treaty must include concrete global upstream measures to curb production and regulate hazardous chemicals. 2, it has to contain mandatory global criteria for product design, ensuring recyclability and reusability standards are met worldwide.
Makes sense.
3, the treaty must be allowed to evolve via voting mechanisms if consensus stalls, which would prevent a small number of countries from perpetually blocking progress. And 4, sufficient funding must be guaranteed for developing nations to implement the changes and build new infrastructure.
The positioning of China is so crucial here, given its role as the world's manufacturing engine.
China accounts for a staggering 40% of global plastic production, so their stance is pivotal. And while they've resisted some of the most aggressive production caps, they have strategically distanced themselves from the small bloc of major oil-producing countries that are vehemently trying to water down the text. This positioning suggests a willingness to participate in a binding framework, which is really the first step required for any meaningful global reduction and redesign strategy to succeed.
Now let's move to the most stringent and immediate regulatory environment that's affecting exporters right now. The EU Packaging and Packaging Waste Regulation, or PPWR. This starts becoming mandatory in 2026, and it fundamentally changes product design.
The PPWR is comprehensive, and it dictates European market access. The defining requirement is that by 2030, all packaging placed on the EU market must comply with new Design for Recycling, or DFR, criteria. And it has to achieve a recyclability performance grade of at least C, which translates to 70% or higher recyclability. This isn't a suggestion, it's a hard barrier.
And the mechanism that ties compliance directly to cost eco-modulation, that's what makes this regulation so powerful for changing corporate behavior.
That's the financial lever. The EU will use the Extended Producer Responsibility, or EPR fees, to do it. These fees will be explicitly modulated, so adjusted up or down,
Right.
based on that DFR performance grade. If your packaging design achieves grade A, which is excellent recyclability, your EPR fees drop significantly. If it struggles to meet grade C, your fees skyrocket.
So it makes bad design incredibly expensive.
Exactly. It makes poor packaging design prohibitively expensive to sell into the world's largest single market. And by 2035, the requirement escalates. All packaging must be recycled at scale, which means a minimum 55% collection and recycling rate across the entire union.
And beyond just the design, the EU is forcing the market to internalize recovered materials by mandating minimum post-consumer recycled content, or PCR.
These are non-negotiable targets, and they're designed to pull demand for waste material. For food contact packaging, 30% PCR content is required by 2030, and that rises to 50% by 2040.
Okay.
For all other non-food plastics, the requirement is 10% PCR by 2030, also rising to 50% by 2040. And this is why material streams like that rice husk silica we talked about suddenly become extremely valuable. They help manufacturers meet these demanding PCR targets, or they provide a certified sustainable alternative feedstock.
Are there exemptions?
There are important exemptions, yes, for compostable packaging and for any plastic component that represents less than 5% of the total packaging weight.
The PPWR also attacks inefficiency and outright waste with hard bans and minimization rules.
They are eliminating entire categories. As of January 1st, 2030, there's a ban on single-use packaging for items like condiments, creamers, sugar packets, and those small amenity bottles in the HoReCa, that's hotel, restaurant, catering sector.
And what about e-commerce?
They are attacking the epidemic of error in e-commerce boxes. The regulation stipulates that empty space in grouping, transport, or e-commerce packaging must not exceed 50%.
That 50% empty space rule has massive operational implications for every company, doesn't it? I mean, it requires more than just picking a smaller box.
Oh, it demands a complete redesign of the supply chain and packaging operations. Companies often use standardized boxes for efficiency, which leads to all that excess empty space. Compliance with the 50% rule requires substantial investment in new packaging machinery that can sense product volume and instantly cut and form right-sized boxes, or an AI-driven inventory management that optimizes packaging selection based on dimensional weight. This regulation is forcing the replacement of generic packaging with highly customized, data-driven solutions.
And moving across the Atlantic, U.S. federal action is slow, but individual states are driving really aggressive, localized change through EPR and toxic substance regulation.
The momentum is absolutely at the state level. We now have 6 states that have adopted EPR packaging laws.
Yeah.
And crucially, the major states, we're talking California, Colorado, Oregon, and Minnesota, have largely standardized their approach by selecting the Circular Action Alliance, or CAA, as their producer responsibility organization.
PRO.
Their PRO, exactly. And this PRO is tasked with consolidating funding from producers to cover the net costs of improving and expanding the recycling infrastructure in those states.
The states are also leading the way on phasing out specific chemicals, particularly the persistent PFAS forever chemicals.
California is way ahead of the curve with AB 347, which already regulates PFAS in plant fiber food packaging. Now, there is a debate, like the recent veto of SB 682, which would have expanded the ban to items like cookware due to concerns about the availability and affordability of safe alternatives. But the legislative focus on eliminating these toxics, especially for materials intended to be composted or recycled, remains extremely strong.
And Vermont has addressed a surprisingly specific contaminant in their composting stream, the tiny produce sticker.
This just illustrates the granularity that's required for these circular systems to work. Vermont banned the landfilling of organic waste years ago, which means compost has to be clean. And non-compostable plastic produce stickers are one of the most common microcontaminants that reduce the quality and integrity of the compost.
I can imagine.
So Vermont's new regulation requiring non-plastic compostable stickers, often made of natural fibers with a certified food-grade adhesive, it solves a small but really pervasive contamination problem. It's necessary to keep their organic waste stream truly functional.
So this overwhelming regulatory pressure is being internalized by the largest global brands. How are they adapting their massive operations?
They're responding with defined, time-bound targets that focus on the reduce and circulate parts of the circular economy. Unilever, for instance, is prioritizing reduction. They're aiming for a 30% reduction in virgin plastic by 2026, and that rises to 40% by 2028.
And they have to be honest about where they're succeeding and where they're failing.
That's where the transparency comes in. They report that 57% of their total plastic packaging is currently reusable, recyclable, or compostable. However, they highlight a massive disparity.
Which is
76% of their rigid packaging meets those criteria, but only a sparse 13% of their flexible packaging, the pouches and the films, does. They openly acknowledge the technological gap in flexible packaging recycling, and they're actively calling for that legally binding UN global treaty because they see systemic regulation as the only way to meet their own goals for these hard-to-recycle formats.
and what about a company like Nestle?
Nestle shares the ambition of 100% reusable or recyclable packaging, and they're making significant measurable progress. They're reporting an 89.5% actual recyclability rate by 2024 and an 86.4% rate for packaging that's designed for recycling. Crucially, they've already achieved a 21.3% reduction in virgin plastics by 2024, and they're integrating 30% recycled content into their plastic packaging, actively driving the market for recovered materials, really in anticipation of those EU mandates.
So what does this massive, escalating regulatory landscape actually mean for a company that's trying to export a product across multiple borders? It means compliance is no longer a paperwork exercise. It's a technical necessity. And technology is now the indispensable tool for managing all this complexity.
The reality for exporters operating in this new landscape is what compliance managers jokingly call spreadsheet hell. Non-compliant products, even with just minor certification errors, risk fines, blacklisting, or even port seizure Japan and Singapore, are particularly aggressive in their enforcement.
So these certifications like EN1 34 through 2 for the EU or BPI for the US, they're essentially passports.
They are the essential passports required for market entry, and this compliance now requires mandatory digital registration before products are even produced. EPR registration is mandatory for the EU. You need your registration with systems like Loose ID. These aren't paper forms. They're digital accounts linked to specific product types and volumes.
Right.
Exporters have to provide QR code linked certificates and online verification links because importers and customs are moving toward digital databases for instant verification. The biggest export weapon, ironically, is audit-ready digital traceability.
Let's discuss one innovation that's designed to address both this compliance confusion and the lagging infrastructure: the BPI's Home Compostability Certification Program.
This program, which is officially launching December 1st, 2025, is a major step toward addressing consumer confusion and the huge infrastructure gap. Food scraps are the largest component of U.S. landfills, and they contribute heavily to methane emissions. Building massive industrial composting facilities would cost an estimated $14 billion.
Wow.
But home composting offers immediate climate action.
But home composting is notoriously variable. You've got lower, less controlled temperatures, inconsistent moisture. How does the new certification account for that?
It creates a scientifically rigorous framework specifically for products that break down safely in those lower, less controlled temperatures of a backyard compost environment while still meeting existing standards for feedstock safety. By linking commercial and home compostable certifications, the BPI builds consumer trust, it ensures clearer labeling, and it combats accusations of greenwashing. It guarantees products are free from harmful components like PFAS, carcinogens, and heavy metals. It really sets a new standard for degradation performance in a decentralized setting.
And given this complexity, where regulatory requirements are changing constantly and certification has to be instantly verifiable, companies just can't manage this manually. This is where AI moves from being a buzzword to an essential operational tool.
AI systems are absolutely becoming the crucial export weapon because they automate the standardization and verification required for global trade. They eliminate that spreadsheet hell and the risk of human error.
So how does an AI actually verify a certificate?
It automates verification by connecting directly to the issuing body's databases via APIs. An AI system can instantly cross-check an incoming shipment certificate number against, say, the BPI or the TÜV Austria database. It ensures the certificate is valid, not expired, and hasn't been forged or repurposed for a non-compliant material. It provides an immediate, audit-ready trail that human compliance teams simply cannot match for speed and accuracy.
And what about staying ahead of the regulatory curve?
AI functions as a real-time regulatory monitoring system. These AI-powered tools continuously scrape, synthesize, and analyze updates to global packaging laws, PPWR amendments, new EPR deadlines, updated chemical bans. When a law changes, the system instantly alerts the compliance teams, detailing how that change impacts their specific product portfolio in specific markets. It allows them to adjust documentation or sourcing before a non-compliant order is even shipped.
This must be invaluable for managing large B2B sales and customs audits.
Absolutely. AI manages the entire document lifecycle. It organizes, tags, and archives all compliance-related documentation instantly. This allows companies to generate comprehensive, audit-ready traceability chains and compliance reports within minutes for customs agents or demanding B2B clients.
And it can even assess risk.
Yes, it can generate a risk score for every single shipment based on factors like certificate expiration, recent regulatory changes in the destination country, and the historical rejection rate of similar products. This allows high-risk orders to be flagged and held for manual review before they even leave the factory floor, minimizing costly, embarrassing, and reputation-damaging port seizures.
Now, shifting from these digital compliance mechanisms to end-of-life solutions, let's look at the rapid growth of the reusable retail pod loops market.
This market is forecast to grow at a really robust 10.4% compound annual growth rate through 2036. It's a closed-loop system pioneered by companies like Loop and IFCO that prioritizes durable packaging, which is purchased, returned, cleaned, and reused dozens or even hundreds of times. This is being driven by regulatory pressure favoring reuse, strong brand ESG commitments, and a rising consumer preference against single-use products.
What have pilots shown us about consumer behavior in these closed-loop systems? Is it working?
Well, the Berlin pilot, which uses shared, standardized reusable containers and reverse vending machines based on the RSVP blueprint, offers some clear insight. And the defining factor for mass adoption is convenience.
It always is.
Always. Early results show that 84% of surveyed customers reported that returning cups via a highly convenient reverse vending machine dramatically increased their willingness to choose reusable cups over disposable ones. This suggests that if the return infrastructure is as ubiquitous and easy as, say, bottle deposit schemes, the challenge of consumer behavior adaptation can be overcome.
But the infrastructure and logistics challenges for reuse must be just immense.
They are. The high initial capital expenditure for the durable packaging and the complex cleaning facilities presents a major barrier to entry. Standardization is also a huge technical hurdle. Supermarkets and distribution centers rely entirely on established barcode systems for inventory and checkout, whereas many of these new reuse systems use QR codes for digital tracking and deposit management.
That sounds like a systems clash.
It is. And the EU's upcoming packaging regulation will require all reusable packaging to carry scannable digital identifiers, which forces standardization but requires a massive, costly alignment across the entire CPG and retail industry. Logistics for cleaning and maintaining the integrity of hundreds of thousands of identical containers across a city is a science unto itself.
So this deep dive has really shown us that the future of packaging is not relying on a single silver bullet, but on two simultaneous complementary pillars: optimization of existing waste and regeneration through new inputs.
Exactly. We're seeing this high-value waste conversion turning agricultural byproducts like rice husk into certified chemicals, construction inputs, and clean energy. And at the very same time, we're pioneering breakthrough regenerative inputs, like seaweed, which bypass the land use pressures that plague traditional bioplastics.
And crucially, we've seen that none of this innovation is happening in a vacuum. It is being violently accelerated by complex, escalating global regulations, from the EU's PPWR demanding mandatory 70% recyclability to the UN pushing for chemical limits on plastic production.
The biggest insight here, I think, particularly for exporters and high-volume manufacturers, is that compliance is the new premium. Certification like EN 13432 or BPI, mandatory EPR registration like LUCD, and digital traceability. These are not just burdens, they are premium value adds. Products that are certified, regulation-ready, and backed by robust digital paperwork are commanding a significant advantage. They're often securing 15 to 25% higher export prices simply because they de-risk the buyer's supply chain and ensure market access. Compliance defines profitability in the circular economy.
We've established that for many of these next-generation materials like PLA or bagasse, home or industrial compostability is the intended end of life. But widespread dedicated composting infrastructure is still lagging, and we still have these major performance gaps in new materials, specifically that need for a 2 to 5 orders of magnitude improvement in water vapor barrier for seaweed films to handle dry food.
And this raises a really important question for you, the learner, to consider. We know that cutting-edge materials like PHA are emerging, which are fully compostable even in marine environments. So considering the technical performance hurdles that remain for most new bio-based films, that massive WVP gap and the lack of elasticity? What specific combination of material science breakthroughs and mandatory scaled recycling or composting infrastructure investment will be necessary to truly close the loop on hard-to-package products, like flexible pouches and thin films, over the next decade? Is the answer radical chemistry, or is it radical concrete, or is it both?